Yes. I tried to have WhatsApp call, but he's not receiving the call.
Okay, no problem, sir. We can start. I'm going to start the session. No problem. So, good afternoon, one and all. On behalf of Janardhan Singh Foundation, JS Foundation, that is, and Association of Indian Physicists, AIP, I, Dr. Sanjay Kumar Singh, founder president of AIP, heartily welcome you all. I also welcome Dr. Captain Vipra Singh, with the today's speaker, will deliver the talk, and the today's session will chaired by Mr. Yugen Atul Kulkarni. I will take maximum 10 minutes to uh, discuss some feedback received by all AIP family members. So next slide, please. First, I will discuss about thanks, appreciation, and something like that. Dr. Captain, next slide, please. Yeah, thank you. So as we have shortlisted around 75 members who have given uh, appreciations to our initiative, like Amir, you all are doing good, and I can just admire your works. Like Divya, Modvil, amazing work. Dr. Usha, you are doing great job, and Mohit, good initiative. So we have received lots of appreciation from our AIP family members. Next, please. So I would like to thanks to all members who are appreciating our work and who have joined our association to contribute the society in any manner, either in scientific or academic. Uh, we all are very grateful to all the members to join here and to connect with on social media. Right. Uh, so we have received this suggestion, Abhishek Kumar. Suggestion is communication should be done only in English, not bilingual. So the remarks on this suggestion, because we cannot exactly do the in one language, we should offer both the language, because most of the people are from North India and South India, so we should bother the things as usual in both language, as per even as per suggestion from our audience, right? So the next suggestion is from Amrit Sagar. He's also appreciating, and he is demanding for some demonstration virtually or physically. So I hope we will plan something like that demonstration in this month of July. And next is Anirudh Singh. Yes, please arrange something on QFT, quantum field theory in the request. Anirudh, we will also plan for this type of uh, activity on QFT, some lectures on this QFT. And another one is Anjali Chauhan. Please try to arrange offline talks also in Delhi, as it helps us a lot. Since we are very few members in as a council members, so we are planning something like offline activity in October. Of course, we will meet. I'm not sure about Delhi, but we can plan north area. Next one is Ankit Kumar. I think so. Ankit Kumar. Please organize an event with 3 lectures in a day. Of course, we can do event in a day. We are planning in this type of event in October, most probably in October or in August. offline event will be in October, and that online one day event that will be in most probably in August. Anshika, would be really great if you could help in career related issue and clear doubts. तो इसके रिगार्डिंग मैं कहना चाहूंगा कि सॉरी so next talk will be on career regarding. We are planning to discuss on how to crack net examination or state level examination. So next talk will be like that. And next suggestion of I'm new to this group, but I think it's a good platform to help us many to learn about physics and their interest. And 1 hour very enthusiastic EIP family member with G Balaji, whose interest is to attend all the events dedicatedly, sincerely. We are very grateful to have like that type of people. Next slide, please. Can we have discussion on innovative activities? Of course, we can have discussion on innovative activities in future. We are segregating all the members in different groups, and we can plan in future. Of course, we can plan. And some persons are requesting from certificate for attending the event. So as you know, we are limited members in council. So we cannot provide certificate, and why we are not able to provide certificate, because our aim is not to provide certificate. Our aim is to develop temperament or provide some platform or provide some material, study material or lectures or platform to do some to enrich the knowledge, right? In future, we can plan if the council member will engage, and we can share the work with each other, right? Ms. Namrata ma'am, organize a manual meet of all the members manually. Of course, we can plan this type of event in future. Mr. Sangam Pasayat, if possible, then arrange some workshop or schools in the field of scientific research. Of course, we can plan. We are planning for workshop and scientific research for faculty as well as the students in future. So we are all the events activities of AIP are in pipelines. In future, we can do all the things with each other. Nikhileshwar, we please let people know each other. Of course, we can plan this type of event in which peoples of the AIP, members of the AIP can interact with each other. We will open that WhatsApp platform to interact with each other, and to even we can share the information regarding that persons who are involved in the research particularly. So I think we have 1 minute. I'm not going to take more than 15 minutes, and after that I will request Dr. Captain to start the or Mr. Atul Kulkarni to start the session. Remaining queries and session queries are will be discussed in next talk. We are working on all the queries, feedback, suggestions, and we will incorporate. We will implement those which are possible. Right. So thank you so much. Over to you again, sir.
Yes, thank you, sir. Deepak sir has joined, I guess.
I think 56 people, more than 56.
Yeah, I have a network issue. That's why I'm not able to join timely. Sorry. Extremely sorry for
Okay,
that.
no problem, Mr. Baker. So, you can, sir, you can
Okay.
start the session.
So I will not waste much time, and I will introduce today's speaker, Dr. Captain Rituraj Singh. He is working as a postdoctoral fellow at IIT Indore, and his research mainly includes the investigation of quark-gluon plasma in ultra-relativistic collisions or collision energies at Large Hadron Collider, which is at CERN. Uh, this work mainly is in nuclear physics or particle physics. He also developed a model named UMQS to obtain Corconia suppression in AA, PA, and PP collisions. So his work mainly based on particle physics, but he also working or he is also interested in astrophysics and astroparticle physics, which includes cosmic rays, neutron star, dark matter, etc. And apart from all his research work, he is also active member of our association. So without wasting much time, I request him to deliver his talk. Thank you.
Thank you so much, Eugene, for the nice introduction. So I will share my screen. Okay. So is my screen visible to all?
Yes, sir.
Yes, sir.
Yes.
Okay. So very good afternoon to everyone. My name is Captain Suraj Singh. I go by the name Captain R. Singh. I'm a postdoctoral fellow, as Eugene will introduce me. So today of topic of my presentation is an expedition from Big Bang to Little Bang on the quest for an exotic state of matter. So this is about the journey from how we came to this stage, from beginning of the universe. So then exotic state of the matter, that is called Quark-Gluon plasma, that I will talk about this thing, will come later. So that is a matter when everything was in deconfined state or detached from one point to other. And then we got to this stage. How we came from this point, from that initial stage to this point, this talk is all about these things. So my talk is divided in three parts. So first, I will talk about the origin, how we started our expedition, then what is helping us to investigate that kind of phenomena. So the big machine, the large hadron collider, I will talk about it a bit more. And then what we have observed in these experiments at a large hadron collider, that I will discuss, and what theoretical models I have developed, that I will discuss in chapter 3. I named it connecting dots. So in connecting dot means my work is to explain the experimental data, what is happening. If you get some kind of pattern, what is the physics behind that, and how we are addressing this. So that is my aim. So here is simply then GIF is a picture of how particles are colliding in a large hadron collider. So that's that's why I have put this here. So now we start from the chapter 1, the beginning. So beginning how, so like it is not very well known, it was not very well known before 1800th century that what is the fundamental building blocks of the matter. We didn't know. Okay. So around 1800th century, names are unknown. So atom was discovered. So now people know that molecule is made up by atom. Some atoms are connected and they made the molecule. Right? So later in 1800th century, J.J. Thomson discovered electron. So you all know the history. So I will not go in very detail. Then Ernest Rutherford discovered nucleus and proton through alpha scattering. So that you all also know. From 1990s. So it took around 100 years from 1800 to 1900 to discover electron, proton, then electron, proton, and nucleus. Okay. So after discovery of atom. Then James Chadwick discovered neutrons, so the neutral particles. So okay, so almost the picture of atom was clear. So like this is the nucleus in the center, and we have a electron cloud around the nucleus. But there were other questions. So okay, we have developed that this is the electron, proton, and neutron, and this is the picture of the atom. But what are the forces or interaction which binds electron, proton, and neutron together in a small size or inside of atom? Okay, how it decreases stable? So from electromagnetic interaction, we know that opposite interacts and similar charges repulse. So, so nucleus, we have all the positive charge. How nucleus is stable? Why all the protons are not tearing apart each other, right? So this was the question. This all question. And reduced beta decay. Why beta decay is happening? Why so the experimental data and theory, it was not going parallel one to other, because experimental data was showing something else and uh, theory was saying something else. So the radioactive beta decay was a puzzle to explain. So now the answer came in the theories. So so the electromagnetic interaction explains electron binding the nucleons. So now we know that electron have negative charge and nucleus have positive charge, so they are bind together through electromagnetic interaction. Okay. So, and Heisenberg and Yukawa came with the theory of meson exchange. So they said that within the nucleus, protons and neutrons will bind through the exchange of meson. So the Yukawa's meson exchange theory. So that's how strong this protons are binded in, are combined inside the nucleus. So the stability of nucleus explained up to the some extent, but the weak force, what is the weak force and how it acts, we didn't know. So because it was very important force, so it was unknown. It was not completely explained. And Fermi theory of beta decay, Fermi theory introduced the neutrino using Paul's hypothesis. So neutrinos are particles which are okay. So someone asked the question, but I will address all the questions at the last. So Pauli hypothesis, using Pauli hypothesis, Fermi proposed the theory of beta decay, how it is happening. So he said that neutrino are the particles which are involved in beta decay, and there is a weak interaction. So this is happening because of weak force. So, but it was not complete picture yet. So there is still some question remains, unanswered question remains. So what are the responsible particles for beta decay? Okay, beta decay is happening, means protons are going to decay in electrons, but how? Right? They are different. So, and how neutron is in neutral particles? Why it has finite magnetic moment? It shouldn't have, because if charge is neutral, then it would not react. It's moving with some velocity. Okay, like electrons. If electron is moving, then we have magnetic field because it has charge. Proton has charge, but neutron doesn't have any charge. So that is why it is called. So it was a challenge. The finite magnetic moment of the neutron was a challenge. So it was considered weak force is stronger than the electromagnetic force. That was also not true. So it was the presumption before the further study. So the true nature of a strong force. So a strong force is the force which binds the protons or neutrons within the nuclei. So true nature, what was its true nature, that was still not very well explained, or because experiment was saying something else and theory was proposing something else. So they were not very well agreeing with each other. Right? So from understanding point of the view, nucleus was a blind spot till 1960s. So like we have developed atomic bomb in 1955 and Hiroshima and Nagasaki, everyone knows. So, but still the true nature of strong force was still unknown. Okay. So the new era began after 1960s, and Gell-Mann and Gell-Mann Quark model and Niemann SS. So they proposed a theory that the proton have internal structure, and they have used especially unitary group theory. So that is mathematical group theory, which is based on this is called SU3. So there are many SU3, SU2, and U1 that I will discuss later. So using these theories, they have developed that there should be an internal structure of protons. So there are 6 types of protons, 6 types of quarks, which combine, which is bound within the proton. So they have proposed an internal structure, and there what they have proposed was confirmed in deep inelastic scattering, which was performed in Albion lab in US. So through deep inelastic scattering, people have found that proton have internal structures. What they have done in deep inelastic scattering, they bombarded beam of electron in the nucleus or in the proton. So as proton have quarks, and quark also have electric charge, plus minus both. So when electron will propagate through proton, it will interact with quark. So its path will differ, like it will deviate from scattering will happen within from this bombardment. So because of that, it got confirmed that proton has some internal structure, so that all the electromagnetic interaction happens through a virtual photon, right? So virtual photon is a photon which are simply fluctuation in electromagnetic field. So they are, according to uncertainty principle, their mass is much higher, so they decay very less time. So their detection is not possible. So they decay in the leptons. Leptons are electrons or muons. So there are terms I will discuss all these terms later. Okay. So now this was confirmed, but first of curiosity again read the question. So it was fine. We have understood the that proton have some internal structure, neutron have some internal structure. Electrons are still a elementary particle. They don't have internal structure till now, right? So, but there are a few other questions. So the question now is the strong force between quark inside the nucleon similar to the force between nucleons? Nucleons are protons and neutrons together called nucleons, right? And the quarks, which are quarks and gluons, quarks which are within the gluons, I tell I forgot the gluon. So quarks which is within the protons act differently. Okay, and nucleons interaction will be different. So what we are assuming that is strong force within the protons, or is actually not a strong force, it is called a residual strong force. And actually strong force is within the protons or nucleons. So, and what kind of the carrier particles bind these particles inside the hadrons? So quarks are there, okay, but what are binding these quarks? So they are also charged particles. So what are these particles? There's another question. And are they analogous to photons, which bind the electrons to nuclei inside that? So as I told, so electromagnetic interaction are generated by through the exchange of virtual photon, right? So photon is a carrier particle. These are called gauge bosons. So it's those bosons, so like photons binding the electron from like charge from positive to negative. The quarks within the nucleus are bind by similar kind of force. That is another question. So if yes, why a single quark does not exist in nature? Like we know that photon light is coming. So that is photon is quanta of light, right? And so but nature single quark cannot exist. It does not allow. But why? So that we will discuss. So to address all these issues, a standard model was started. So there are some, I have only addressed 3 points. So standard model characterize all kinds of particles, fundamental particles which are responsible for this universe. Okay. And the standard model proposed that all the force fields, like there are 3 kind of fundamental force fields, strong force, electromagnetic force, and weak force. Gravity is not a force as per GTR theory, so I have not incorporated gravity in this work or in this slide. So how these 3 in the standard model, gravity is not part of the standard model. So all these 3 forces are generated by the exchange of the vector gauge boson. So like we have quantum mechanics. So standard model is based on the development of the quantum field theory. Okay, so like electromagnetic force, we have quantum field theory called QED. And then for weak force, we have quantum field theory called fluorodynamics. And for strong theory, we have quantum field theory called quantum chromodynamics. Okay, so QCD, quantum chromodynamics, proposed color charges. So like plus or minus, they are electric charges. Similarly, they are color charges which bind the quark and anti-quark within the nucleus. So like delta plus plus is has the 3 up quarks, which is a particle observed in collider experiments. So delta plus plus has 3 up quarks, u. So like we know from uncertainty principle, more than one particle cannot stay in same quantum of state. Okay. So how 3 particles are there? So they introduce 3 colors: red, green, blue. So they said all 3 particles have different 3 colors. These 3 are quantum numbers. So that's how they have introduced the color charges. So now here is the net chart of the this particles. So these are first generation particles. So they have spin half. So this is the quark, U quark and D quark. These are the charm quark, second generation particles. Charm quark and strange quark. The top quark and bottom quark. So these are 3 quark, which are responsible for strong interaction. Okay. Now below we have electrons. Second family of electrons is muon and tau. So here mass is increasing. So electron is the lighter one, and muon is bit heavier than electron, and tau is most heavier electronic particle. And corresponding to respect to them, they all have neutrinos. So here we have electron neutrino, muon neutrinos, and tau neutrinos. So these neutrinos are responsible for the beta decay. So in every beta decay, these neutrinos are involved. And universe, we every per second, every second, billions of neutrons are passing through the Earth. So they barely interact with matter. They are massless as per its theory of standard model. But recently, neutrinos got the discovery of neutrinos got the Nobel Prize, showing the neutrino has some very finite mass. But why they not have the mass? The theory lies here. So here is the fundamental particles which introduce all these forces. So strong forces, the red line correspond to strong force. So gluon is the mediator particle which generate the strong force. So there are 8 types of the gluon. It has spin 1, which was shown. This is the photon. This is responsible for electromagnetic force. So anywhere you have electric charge like plus minus charge, photon will be there. Okay. So it has spin 1, also photon, massless. This is also massless. Now we have weak interacting particles. So these are 3 particles: Z0, W plus, and W minus. They are very heavy particles, and they interact. So this CN, this thing diagram line is showing that weakly interacting particles are this thing. No, sorry, this line, green line. Yeah, not green, blue line. So blue line is for Z0, W plus, and W minus. So the particles which are incorporated in electromagnetic interaction. No, sorry, a weak interaction. So like muon, sorry, neutrino, neutrinos, electron, and quarks. They all are incorporated in weak interaction. And Higgs boson, Higgs boson is the particle which gave the mass to all the particles. So any particles which interacted with the Higgs boson got the mass. So like we know that from 2012, the Higgs boson got the Nobel Prize. So their Higgs field or any particles which interact with the Higgs boson receive the mass. So neutrino do not interact with the Higgs boson. And this photon and gluon, gamma photon and gluon, they also do not interact with the Higgs boson. So that's why in standard model, these 3 particles like gluons, photon, and neutrino, they are massless. Except that all the quarks and electrons and W and G bosons are massive particles. So these are characterized in 1 and 2, or 1G, 2G, and 3 generation factors, depending on their mass only. Okay. So from matter to
Captain, can I ask a small question?
No.
Because I'm curious.
No. Later you can ask. Please.
Okay.
Okay.
Mhm.
Please do not interrupt. Okay. So matter from molecule to quark. Okay. So what we understood till now from large to small scale, that this is the human body. So we are made in many things, iron and everything in our body. Okay. So if we go, DNA is there. So DNA is made up by molecules. Then within molecules we have atoms, and within atoms we have nucleus. Okay. And then nucleus we have quarks, protons and neutrons, and this proton within protons we have quarks. So like here's how quarks are interacting. Okay. So in better picture you can see here. So it's simple again presentation of that thing. So molecules, then atom, electrons are surrounded by nucleus surrounded by the electrons, and then nucleus, and then proton and neutron. Then gluons are the binding particles. So this tube or this tube is connected to the 3 quarks within the proton. Okay. So now coming to the standard model. So all these things gathered, all information gathered, and standard model was proposed. So the standard model is a gauge invariant quantum field theory. It combines the products of the unitary products of SU3, SU2, and U1 to explain the true nature of the building blocks of the matter. So SU3 is the theory of strong interaction. SU2 is the theory of weak interaction, called especially unitary group 2. And U1 is the theory of electromagnetic interaction. So from special unitary groups or unitary group, or every unitary group has a generator. So here SU3, SU2, so generators are designed at n square minus 1 for SU groups. So like if you square 2 square, 2 square is 4, 4 minus 1 is 3. So as you have seen in the last picture, here that we have 3 generators. So we are the generators of the force field. Okay. And SU3 means 9. 9 minus 1 is 8. So we have 8 types of the gluons because of that. And U1 is only 1 photon. So there is n square. So because of that, we get only 1 photon in this picture. So the strong theory of QCD predicts that under extreme condition, there is a chiral symmetry restoration. Chiral symmetry restoration, we say that quark in the unbound state are massless. They don't have any, they do not acquire any mass. So these two are coupled, SU2 and U1. They have coupled in one framework called quantum fluorodynamics. But SU3 is still struggling with combining with these two. So to know the better behavior of the strongly interacting medium, we need to go its early phases, where it was in deconfined phase. So that deconfined phase is called Quark-Gluon plasma. Okay, so the standard model, so as I said, standard model advocates the existence of Quark-Gluon plasma at very high temperature and very high baryon density. So like quark, proton or neutron, they are called baryons. Okay, so that's why if you have high baryon density, mean high number of protons and neutrons as in general. Okay, so but what is the Quark-Gluon plasma? I said okay, Quark-Gluon plasma is there. The Quark-Gluon plasma is thermalized deconfined phase of strongly interacting partons. So here I have told the gluons and quarks, they are within the protons. Okay, so there is a phase where all protons boundaries are melted and we have free quarks and free gluons. So that is called Quark-Gluon plasma, and it is thermalized, it is in thermal equilibrium, and so a similar kind of collective behavior. So, but what is the collective behavior? Question is what do we mean collective behavior? So here is a collective behavior. So like भेड़ चाल, you know, सब एक डायरेक्शन में जा रहे हैं. So this is called collective behavior. There is collective motion. सब एक तरफ जा रहे हैं. Like people moving here, they are moving in one direction. They may not be connected, but they are moving in one direction. So this is called collectivity. Bird flying in same pattern, also called collectivity. Fish swimming in the sea is also so a kind of collective behavior. So we have collective behavior in the nature. So QGP shows a collective behavior. If there is a QGP, all particles are strongly interacting. They must show a collective behavior. So that is the definition of Quark-Gluon plasma. Now, so this was a Quark-Gluon plasma, but why Quark-Gluon plasma is possible? What happens at high temperature so that we get the Quark-Gluon plasma? So the QCD says that at large momentums, so there is a coupling constant, like there is strength of binding the particles. Like we are coupling two balls और किसी को बांधना है, तो रस्सी कितनी मजबूत है ना, इस पे डिपेंड करेगा उनका बॉन्ड कितना मजबूत होगा. तो वो स्ट्रेंथ ही है कपलिंग कांस्टेंट. तो रस्सी कितनी मजबूत है इसका एक्सप्लेनेशन देता है हमारा कपलिंग कांस्टेंट. So this coupling constant gets weaken at a high momentum transfer. तो अगर ज्यादा एनर्जी ट्रांसफर हो रही है, then what will happen? वो बॉन्ड कमजोर हो जाएगा, वो रस्सी कमजोर हो जाएगी. So that's how, अगर ये रस्सी कमजोर होगी तो सब कुछ ब्रेक हो जाएगा, है ना. Asymptotic freedom is a QCD property. So what asymptotic freedom says, at small distances, so we have one kind of potential which says that small r potential becomes almost negligible. So particles gets free. There is no boundation, right? So this particle gets free. So that is the asymptotic freedom. And at some point when initial, so there is chiral symmetry restoration. What is chiral symmetry? Like every particle has different mass. I have shown you 6 types of quarks. So in bound state, they have different mass, bare masses. But in free state, where they are deconfined from one another, they all are massless. So when they bind, the dressing of the gluons generate the mass. Without dressing of the gluons, these quarks are free and massless. So you cannot distinguish which one is the which quark. This is which one is up and which one is down. So that is called chiral symmetry restoration. So in bound state, you can distinguish. That's how chiral symmetry gets there. So as of now, we know that our body is made of all these protons, neutrons, electrons. But some point when they were detached or they were not bind, so there would have been an any stage. So that is an indirect hint that QGP would have been there in initial stage of Big Bang. So the Big Bang theory of early universe expansion implies that if we reverse the math of acceleration process, the universe will reach at the very early phase. So QGP came into existence just after few microseconds of the Big Bang that I will show in next picture. So at that time, matter density and energy density too much high that it was that much high that we cannot imagine. Okay, so this is the big picture. How we came to this phase, okay, of universe from this Big Bang. So here we are in this phase where we are trying to create a little bang through the collision that I will discuss in coming slides. And this was the phase where actual Big Bang was happening. So this was a time of inflation. So here is the time. So it started for time 0 to 10 to where time of 10 power minus 44 second, 10 power minus 37 second inflation was there. After that, QGP came from this phase to this phase. This is QGP. Here, dark matter particle was appear and then disappeared also. So this QGP existed from 10 to power minus 37 second to 10 to power minus 6 second, 10 to power minus 5 second. So it was too quick. You cannot imagine that 10 to power minus 5, 10 to power minus 10, very small time. Small is in our imagination. And after that, matter came. So here, particle got combined, quark got combined to form hadrons. Hadrons are called proton neutrons, or mesons are called hadrons. Okay, so quark anti-quark bond in states called mesons, and quark anti-quark or normal quark combines are called 3 quarks, so more than 3 quarks, like 5 quarks. They are also called baryons. So baryons and quarks, the mesons were formed. Okay, these are the neutrinos, electrons, photons. It was coming from there. It was there. After some, so it was matter was formed, but it was in separated, but didn't form the atom yet. So now here we got the nucleus. So atom is all the hadrons tried to club together. They were coming together and forming the nuclei. So nuclei form. Electrons are still not combined, and here in the present this scenario, electron atoms were formed. Okay, so like you see the nucleus and the electrons are revolving around. Okay, so it took 10 to the power 9 years, so that you can imagine 10 to the power 9 years is how many years in billion years. So from Big Bang, so it took from time 0 to 10 to the power 9 years to build the first atom, and then after atom created or molecule was also formed, and then creation of the nebula, galaxies, the stars formation, everything happened, and then we are here. So it took us 9 years to come to this stage. Okay, so here we are. So at this point we are trying to go this phase, which is a very difficult task, and that's okay. So that's how we can do. So we are in this phase, and QGP came into this phase. We want to probe this phase that Quark-Gluon plasma was there. So to better develop the understanding of the quantum chromodynamics, or matter which is strong interact through strong interaction. Okay, so we need to go backward in time. So this is the nature. So we were there in early Big Bang, then few microsecond QGP came to picture, and atom and molecule, atom, everything came here. Now in experiment we are trying to go back there, but how it is possible? So that's how our machine is helping here. So here the Large Hadron Collider comes into the picture and try to create the matter which was existed before, after just microsecond of the Big Bang. So now I coming to the chapter 2, the big machine. Here I will talk about the this Large Hadron Collider and CERN. So the Large Hadron Collider, or it is called LSC, pushes back the frontier of knowledge via accelerating the science. Accelerating the science is the tagline of the LSC. So what is happening after each collision? It has opened our eyes that the physics is much beyond than our imagination. So many new things came up. Also stepped into the dark matter sector, dark energy sector. So CERN is working. Is helping scientists to understand the nature in very good manner. So it's the world's largest particle collider experiment built by a CERN. So what is CERN actually? The CERN was built in 1954, developed by, funded by European society, named as Council European pour les Research Nuclear. So this is called CERN. Yeah, so over 60 years, it is working for humanity and increasing our understanding of present universe. So India is also a very important member of the CERN, and it has 22 member states, European Union, and all over the world, all the countries have joined the CERN. And it is the only experiment, CERN, which received the Science for Peace award from the United Nations. Now, developed new technology for accelerator and detectors. They are also used in other field of science. So, CERN has also given us many things we don't know yet. So that I will discuss. So now, what was the first objective of the experiment? Why we build the Large Hadron Collider? So, as I told, we wanted to study the uh, sorry, we wanted to study the basic nature of the matter, strong interacting matter. To do that, we have built the Large Hadron Collider. And what is the microscopic mechanism responsible for them? What are the microscopic degrees of freedom or excitation of the matter at ultra high temperature and density? So bound nuclei form or at atom is formed. What happens when we increase the energy or temperature or or matter density? What happens at that stage? Like neutron star, what happens there? The matter density too much high, like one spoon of the neutron star, one spoon mass of the neutron star, much heavier than our Earth, right? So, what is happening in that critical situation? And how did its properties influence the evolution of the early universe? If QGP came to existence, is there something is it changed or how it affects the evolution of the universe? And how hadron acquire the mass, how is modified by the medium it moves in. So this was the aim, and its objective got completed through the journey through the discovery of the Higgs boson. So it was proposed in 1960 by Peter Higgs that there is a particle called Higgs boson, the quantum of Higgs field, and through this which all the particles will interact and will get the mass. Okay. So similarly, so that was the objective and it got fulfilled, it got completed. So, and what is the structure of nuclei when observed at a smallest scale with highest resolution? So the LSC gives us a very high resolution collision. Luminosity is very high at LSC. So it works in many domains. Dark sector also is the part of this LSC. So I will come that later. So this is the Large Hadron Collider. It is 27-kilometer ring. It is below underground in the Jura Mountain and Alps in the Switzerland, Geneva. So this is Geneva Lake. So it has four experiments. This is LSCB. One is this is sorry. This is Alice Atlas. This is Alice, and this is CNS. So all these four experiments are dedicated for different purposes. Like Alice is basically dedicated for investigation of the Quark-Gluon plasma or the uh, working of the early universe. Okay. CMS has also some overlapping interest. Okay, so it also works on Quark-Gluon plasma investigation and some other fields also. LSCB is dedicated to study the um, heavy particles like bottom or top quarks. They are very heavy particles and they are boundary states. And also working on dark matter sector. And Atlas also similar kind of high PT particles. So there are many technical details that I will not go into. So LSC is basically LSC is basically three key technologies. So first is the particle acceleration. Okay, so there the particle are being accelerated here from here to here. Then particle detection. So after collision, particle will form and collide, and then they get it detected. And then large computing grid. Why computing it? Because without computing grid, we cannot store the data. What happened in these collisions? They produce lots of huge data. Okay. So that is stored in these grids. So this is divided in three parts. So now it's time to watch a movie called Clash of the Protons. So I will stop. I will just will play a video for a better understanding. Please keep watching. So here it is topmost large hadron collider. Now how it's colliding the atoms. So what is happening here from this gas cylinder, hydrogen gas cylinder? They have taken out the hydrogen atoms and okay, so they are stored here. So all the hydrogen atoms are stored here, and the electrons are stored by providing the electric field. So by providing the potential, you store the electrons, and now being accelerated by providing the strong electric field. So they will travel through a beam. This is called LINAC, linear particle accelerator. So it is being accelerating the proton beam. It is gaining the speed as time increases, and so here it is traveling with the 1/3 speed of light, and it will boosted in this ring in 4 bunches, and then booster ring. So in this booster, they will provide the electric field to bend all the beams, and the pulse electromagnetic field to accelerate them. Okay. So they are pulsing. So battery coming up and down is pulse doing generating the pulse electric field. It's like swinging the wire. झूले में जैसे बच्चों को झुलाते हैं ना, झूला जब वापस आया ज्यादा then we push again. So ये वैसा हो रहा है. They are accelerating the particles. Okay. So as we know from STR, special relativity, when we increase the speed, the Lorentz contraction will happen. So so the nucleus gets contracted. That's why we get kind of bullet kind of things. And then we are increasing the speed. Okay. So here in this booster, it has the velocity of 90% of the speed of light. Okay. So as we know that when protons or anything is reaching to the speed of light, after some extent we cannot cross the speed limit, that is c. So what happens? It will increase the mass or energy. Both are so at relativistic limit, energy and mass both are the same thing. So as they cannot go faster, so they are gaining the mass and they are getting heavy. So as we know, the proton has mass 1 GeV. Here they have the mass 200 GeV. So now they are very heavy. Now, so they have another booster because now here speed was 90%. Here they have again pushed it here. Now they have reached the speed of around 9.9 C. And from there, they have ejected into the Large Hadron Collider. So this is called SPS, Super Proton Synchrotron, and this large is called Large Hadron Collider. So now, okay. So there are 2 vacuum tubes where the particles will travel through from, like one is traveling in this direction, another is opposite direction. So, and there is a cut. So in this cross mark, they will collide. And these cross marks are the experiments, detectors called LSC, Atlas, LS, or CMS. So like these are the crossing points. So their particles will collide. Okay. So now they are traveling the speed of light, and then here particles are colliding. So here the protons or nuclei, they are going to collide. now they have collided at this point, and these are the detectors. Okay, and then it will be detected, and data will be stored in these grids. Now, this is a picture of universe evolving from one point to another. So the little bang created here, and then it evolves. Okay, so now coming back to our presentation. Yeah. Okay. So now going from there. So these, as we have seen, these many particles are produced in these collisions, and then it will be absorbed in these detectors. These detectors will detect these particles and then analyze. So there are four kinds of detectors, as I told earlier. So the Alice experiment is dedicated for heavy ion collision and investigation of the early universe. Then Atlas and CMS, general purpose detector optimized for rare process like Higgs boson and other things. And LSCB is for discussing the so here the spelling mistake, the bottom and top walls production and their decay components. So now the interesting thing is that the size of these magnets which is being used at Alice is heavier than the Eiffel Tower. So sorry, I have kept the Alice Tower picture, but this is I think from somewhere else. So this is very heavy, and data which got stored in LSC. We try to store one event data. One event we say when one proton collider. So like if one event data is generated cannot be incorporated even in 20 billion cities. That is, if you put all the cities line by line, one over one, then we wrote 20 kilometers. You can see the scale. This is the mountain. These are the plains, and this is the balloon. Everything. Okay, so it's more than 30 kilometers. Now, this is the image of the LS detector. I have especially shown LS detector because it is dedicated for Quark-Gluon plasma phase that we are trying to investigate to prove early universe. Okay, so you can see how big it is. So here there are the humans which are living here. There are the people, and this is the complexity of this detector. So there's many parts, many technical details that I will skip. And India has major collaboration in the LS experiments. So as you can see here, there are many parts of the country that people have joined the LS. These are the Indian institutions. So people who are interested, students who want to join the high energy physics program, they can take admission in PhD or MS program in all these institutes. So as you can see that from Kolkata, Mumbai, Jaipur, Indore, Guwahati, Chandigarh, Aligarh, even Jammu, Bhubaneswar, all these places are there. Okay. So there are some interesting facts about the LC. So the magnetic field generated at Large Hadron Collider is much more than the magnetic field of the Earth, or even the magnetic field of the of a neutron star. It is around order of 10⁵ Tesla. Okay. So that much magnetic field is required to bend the beam of the colliding ions. So here Lorentz force due to the acceleration of the proton, that is 12 times the acceleration of a gravity. So this is too much. Now the force which is much greater than the acceleration of the gravity. Now each of two colliding beams has these number of protons. You can imagine it 115 to the power 11 number of protons. A huge number of bunch particles, but particles are colliding in bunch. Huge number of particles colliding in bunch. So it generates the force of 26 tons. So you can imagine how giant this experiment is. So the luminosity is also very high. So every second the detectors detect 10 to the power 34 collision in per unit centimeter square per second. So that is the luminosity of the collision. And the heat or temperature generated in these large hadron collider or heavy ion collisions, it's much more than our sun's core. Like it is 6 billion times greater than the temperature of the sun's core, what we have in the core of the sun. So that is around 774 kg explosion of the TN. So now the byproducts, how will this help the humanity? So you use www as of now we are also using. So www was developed by Tim Berners and Lee. Tim Berners-Lee at CERN from 1989 to 90. So they have developed WWE to distribute their data. So they deposit a huge amount of data. They need to distribute all over the world. So they have developed kind of cloud computing grid by which they can share that data. So they have developed World Web Wide. And 1970s, people don't know that 1970s was first time they have developed the touch screen. Nowadays we are using touch screen phones and laptops and everything. So, but it was first developed in 1970s in CERN for their purpose. It was manufactured by CERN and put to use in 1970s. So these are the few. There are many fields and has helped in this community. So, in cancer therapy, accelerator facilities, small accelerator, not LSC, has been used to treat the cancer. Semiconductor industry is also being used. The tone beam welding and cutting, accelerator facilities are being used. And radioisotope production, non-destructive testing, insertion of nuclear wastes, like how to dump or get rid of the nuclear waste. That is for that we use the this thing collider facility. The source of neutrons for like any collisions. So we need the high energy neutrons. We need collider facility. So the source of synchrotron radiation, biology, and social statistics, many more. So like let's see help people in many ways that we don't know. So now coming to the chapter 3 is connecting dots. So I think what you would have been bored till now. So I will make it very short. I won't go much in this. So what we have observed in Large Hadron Collider. So we are in currently we are in this phase, present epoch, where matter is bounded in the nucleus or atom. So this is the present epoch, okay, bounded shared matter, and we came from this era where Big Bang was with there, and matter was in deconfined state. And we are trying to go back into time. So what we have done, we have deployed a huge amount of energy. We cannot compress the matter this phase, but we can provide that much energy that they all get deconfined, or all the boundaries are melted here. So here, this is the matter which is being generated in the heavy ion positions. So how to detect that it happens or not? Because QGP may exist in relativistic collision. There is also one relativistic heavy ion collision facility at BNL, US, and this so BNL was the first, but it has very low energy as compared to LSC. So, but there are So there are two challenges to detect the Quark-Gluon path. First, the color confinement, which is a property of strong interacting matter medium, does not allow it to be observed because it doesn't say that single quark cannot be observed. So because of that, we cannot observe Quark-Gluon plasma directly. And other thing is happens for very short span of time. So in ultra-relativistic collision, UGP comes into existence for 10 to the power minus 24 seconds. So it is very small time, and for that small time, it is impossible to observe it directly. So there are some indirect ways through which we can say that QGP came into existence, it got formed in heavy ion collisions or not. So there are few signatures or probes, we call it probes. So which claim that QGP can come into the picture. And so the Quarkonia suppression is one of the best probe. Other are strangeness enhancement, collectivity, dielectron production, direct photon production, and many more. So Quarkonia suppression is one of the best. So what is the Quarkonia? Quarkonia or Quarkonium is a bound state of the heavy quarks, charm quark and bottom quark. So this is the meson of C and C bar and B and B bar. This is charm quark and bottom quark. It's the bound state of heavy quarks. These are Quarkonia. When they travel through the QGP, they get suppressed. So what do you mean suppression? So what do we understand by the suppression? So suppression happens. So suppression is actually reduction in the production. Like we are expecting something and we are getting less. That is called suppression. If we are getting more, then it's called enhancement. Okay. So what is happening here? Is it visible to all, right? I think that is so. Okay. Hello. I'm audible to all, right?
Yes, sir.
I'm just confirming because I thought the 19 again went on. Okay. So what is happening here? The two particles are colliding. So here there are two colliding ions. They are Lorentz contracted. So that's why they are not spherical in shape or distorted shape. So they are in elliptic shape. So they are Lorentz contracted disk. They collide and creates a fireball. This fireball takes some time to get thermalite and create or melt all the protons to hadrons to make a Quark-Gluon plasma. So the heavy particles which are created here, they usually do not get melted. Okay. So like here 4 particles are expected. Okay. But in QGP we have only 3 particles, and one particle is getting dissociated or killed by other nearby partons or quarks or gluons. So what we get at last only 2 quarkonia, right? 2 heavy mesons. So this is called the suppressor. Like 4 were produced and we are getting only 2. So what we were expecting, we are getting less. So this is called the suppression. So how are they are getting dissociated or decayed in the medium? So here I have simply this one effect of the suppression. So this is hot metal effect. So like this is called color screening. It was first proposed by Swayi and Saj in 1986 by taking the analogy from QED plasma, where like electric charge is streamed out after applying the potential. So like ordinary plasma, QED plasma. So similarly here we have color charges and quarks. So between these heavy quarks, these partons or quarks or gluons will come in between them and then reduce the relative strength. Okay, so color charges like gluons which are binding these two quarks will dissociate, will interact with someone else. Like दो लोगों के बीच में कोई तीसरा आ जाएगा तो बॉन्ड खत्म हो जाएगा. So it is happening there. So they get dissociated and they will kill. So that's how they will dissociate. If they try to escape that part, they will come here. So how they can escape, and so this is my work. So they can escape or they cannot escape, that I try to investigate. So this is my model. I named it Unified Model of Quark-Gluon Suppression. So basically, this is the based on the unification of the suppression mechanisms. So as I told, what is the suppression, and along with the regeneration mechanism. So regeneration is like a rebirth. So something or someone was killed and then got born again within the medium. So this is called a rebirth. So suppression and regeneration both are incorporated in one model. Okay. So through this model, I tried to explain the experimental data. So these error bars are the experimental data, and this is my model study. So I compared my results, suppression results, with the experimental data, and they are quite well agreeing with the experimental results. So this is at RIC, a BNL, and there's LSC at 2.760 TeV. Okay, fit down. This is for thermonium. This is for bothonium, 2.76 TeV. This is also for bothonium for 5.0 TeV. So this is the collision energy. So there are many technical terms which I am not able to explain. I can explain, but I have to cover a lot of things. So I have not covered all these things here. So this is for PA collisions. So what I'm saying that my model tried to explain the experimental data, and we are well explaining all the things. So all those, so our models say that QGP like medium came into existence. So in that observation, experimental results came, and we applied the QGP phenomena. How QGP, if QGP will come into the picture, what will happen? Using all those things, I have developed these models and compare our calculation results with the experiments, and my results are agreeing with the data. So that's how we say that, okay, QGP is formed in heavy ion collisions. So these are the studies I have done. So questions continue. There are many more things to explore. So it will be continued. And so this is the talk, and thank you. I'll end my talk. Yeah, Sanjay sir, begin.
Thank you, sir, for your nice talk. It's a very talk which give a lot of knowledge to the new faculty members as well as the students who are interested in working in the particle physics. So once again, I thank you, sir. So now it's time for the questionnaire
Yes.
discussion. So, Captain, sir, there is a question asked by the Asika Chakrabarti in the chat box.
Okay. Chat box.
Yeah, there is a nice questions in the chat box.
Okay, I think there are many questions. So I
The
should
first,
read or yeah. Uh,
so the question is, when objects like electrons, for example, interacts with the heat field, I mean light certainly dragging through while acquiring its masses, why does it, why does it not slow down due to friction? After all, it is dealing with resistance.
okay. So first of all, it is not like interacting means something passing through. Okay, so interaction happens through the exchange of quanta of photon. Okay, like you are traveling, I gave you something, you gave me something. This is kind of interaction. It is not like that one is dragging in a mud, so that friction will work and this thing. So like it is interacting through radiation, kind of exchange of quanta. So Higgs boson is a quanta that exchange that generate exchange between electron to Higgs field. So there is a Higgs field and that Higgs field exchange interacting with the other particles through the quanta called Higgs boson. So like photons interact in E plus or E minus. So photon is a carrier particle, right? Similarly, Higgs boson is that the quanta of the Higgs field that interact with the electrons. So yeah, friction will not be there.
Next is Priyanka Chaudhary. How it is possible to detect QZP practically when it exists for a very short duration of time? I hope the answer is already given to
Yeah, I
the
have given.
so
I
I
have
hope
given. Yeah.
no need to. Uh, Next is there is a one of the member, Sania Devi, raising a question. Sania, you can ask question, your doubts. Sania Devi. Sania Devi.
Now, Shaina, you have some question? You have raised your hand?
Saina Devi.
Yeah, Shaina. I think it's,
Okay, no problem. There is a question from CB Gupta, sir, in
okay,
chat box.
okay, sir. Can you read, sir, which question? There are many questions actually. So,
Of
There
course.
is from the Srinivas Sandhyala. Can Yukawa interaction theory can be used to explain Higgs field with the leptons or quark field?
I don't know what is the left answer quark field, so I cannot comment about it. And Yukawa theory is different. Yukawa theory talks about the exchange of the pi meson to generate the strong field. So for Higgs field, definitely it cannot be because it has the elementary particles, and Higgs field Higgs give the mass to all the elementary particles, not the bounded states. So when I said so, that is for bounded states. Yeah.
Yeah,
Okay,
there is a
so it is lepton or
Sorry, sir,
quark.
it's lepton or quark field.
Yeah, so yeah, either just so yeah, so you cover interactions for strong interaction. So lepton will not be incorporated. One thing, and for quark field, yeah, Higgs field is already there. So that is within the standard model. Beyond standard, what is happening? That is a question of research. People are working on it. So like his neutrino masses. So within the standard model, neutrinos are massless. But now people have found that neutrinos have finite mass. So that discovery goes beyond the standard model. So people are working on it. So there may be some other theory which can better explain all the statistical phenomena. But currently, standard model is the best as of now.
Yeah, and there is a question from CV Gupta, sir. Before the Big Bang, what was there? From where point of energy came?
Okay, so energy was every. So Big Bang is not like that. Big Bang happens something. Okay, so Big Bang is a fluctuation in the quantum fluctuation. Energy was already there. It was deposited. Huge energy was there. Quantum fluctuation happened, and then Big Bang started. So consider it like a rubber seed, which is very huge. You want to map it. So from which point you will map. So Big Bang is a point from where we say that okay, this is the point. From this point we can map our universe. So with that point, we said, okay, time is started from that point. So everything should be aggregated at that point. And that point is Big Bang. So from that point, time is started. So before that, time is also zero. So we cannot assume anything beyond the time. So the time is zero, then nothing was there. So Big Bang is a point where time was zero, everything was zero, then thing was started from that point. Synergy, everything is accreted at that point. Yeah. That is my answer.
Is there any other question from the
I
audience?
think there is a question from Sampurna Das. I have not understood what is the third evolved question.
So why we are not able to see the in the chat box?
I have not understood what is the third evolved question. So theory of beta decay. Okay. So beta decay, so energy momentum conservation was not incorporated, right? So like beta decay, one proton is going to electron. So what is happening? What particle is involved in beta decay? So W and G boson, so quark do not interact with electron, right? So they can interact with electrons through photon, but quark are very massive, and electrons are very less massive. Okay, like electron has mass 0.5 electron volt. Or quark masses are in MeV range, right? Maybe to GeV range. So when one quark is decaying to electron, so energy momentum conservation point of view, what is happening? And what are the particles? So every exchange there should be a particle. Which particle is responsible for which kind of interaction? So because without the W and G boson interaction, beta decay cannot explain very well. So neutrino hypothesis came. Neutrino was proposed by Fermi by using the Polish hypothesis of neutrinos. But still particle was missing. The interacting particle was missing, and that was the W and G boson. W plus minus G, Z0. Yes, sir. C.D. Gupta sir has asked, have any physical proof of the Big Bang? No, sir, there is no physical proof of the Big Bang. But there are the theories. We have to believe something, or we have to take some one point where to start. The point may be false or true, but that's how an investigation starts. So we are starting our explanation from one point. Okay, then we are explaining, okay, KGP came into existence or not came into existence. Then we will explore that theory is correct or right, but at least we will go in some direction. Maybe right and wrong. If it is wrong, then we'll get experiments will tell the truth. Okay, so theory and experiment to go parallel, we have to go very slowly. So there is no proof, physical proof of Big Bang. Yeah, that is a theory.
There is another question from the Priyanka Chaudhary. Sir, can you explain how CP violet is related to Big Bang?
CP violation related to Big Bang. I'm not sure very much. CP violation is happening in like big decay. Okay, so these are the big decay are the process where CP violation is happening. Okay, but there are other things like baryogenesis and leptogenesis. Okay, like the dark matter, antimatter things where it disappears. Many things involved with are related to Big Bang. So these things need to be explored, and people are working on it. So there are many people working on dark matter sector. I also started working on this thing. Okay. Baryogenesis say, so like in particle physics, then what we say the baryon number and lepton number are conserved. Lepton means electrons, protons, you know. So leptons are lepton number and baryon number are conserved, but there are processes where lepton number and baryon are not conserved. These are called leptogenesis, and baryogenesis. These kind of violations are people are working on. So this is the work comes under the picture of beyond standard model BSM. We call it BSM theory. So BSM supersymmetry and many things, and many things comes in that regime.
There is some question, Balaji, putting that, I don't know where it has. What about the spin of these subnuclear particles?
So yeah, so all they have the spin. So spin is a quantum number. Okay, it is not like something is rotating. So all the particles, in my picture, I think I have shown there. All the first generation particles are leptons. No, sorry, fermions. So fermions, so like all the fundamental particles, quarks, electrons, neutrinos, they are leptons. They have spin half. Okay. And all the gauge bosons, they are bosons. They have either spin 1 or spin 0. Okay, so they all have spin. Spin is quantum number. They all have spin.
If we have no proofs of the Big Bang, then why are we emotional on the Big Bang probability? The question was asked by C.B. Gupta.
Yeah, I do not understand this question. Big Bang probability emotional. There's nothing to be emotional actually. Science does not live with emotions. It lives with the facts. Okay, so they are Big Bang theory may or may not be true, but it gave a hint. And the QGP like, as I said, Big Bang before the QGP like thing happened in the early universe. And experiments are proving that. So there is some proof. We cannot go beyond time of the when t was 0 after 3.4 billion, 3.7 billion years. Okay. So we are at the phase of 10 to about 13.7 billion years. Okay. We cannot go back at the time of the Big Bang. We can predict what was happened. That is what we are trying to do. And with this experiment, like QGP, like medium was explored, it's not very subtle, but 98% or 90%, I say, is settled that QGP like medium came to existence heavy encounters. It is the prediction of QCD. So if it is there, then why how we got the first atom or first nuclei or first proton? There would have been some reason, okay, of some cause that how we get this first proton. So all these theory we need some stamp. That's why we say that Big Bang would have been happy, but we are not emotional about it. I'm pretty sure. If there is better theory, we will look into it also.
Yadu Krishnan, he is asking, I recently saw a video which stated that James Webb Telescope has recently found a galaxy within 650 million years after the Big Bang. Does it indicate the possibility of other Big Bang before that? Because masses started to form much later than that.
Yeah, sure. Good question. So James Webb Telescope, it is looking back into time. And as I said, Big Bang is a point where how to map, like you want to map your land or something you want to measure. You would put an tick, you pin that from this point I'm measuring this thing. So distance. So Big Bang is a pinpoint in the universe. Okay. So yeah, beyond that pinpoint, something could be there. That is quite possible. So what James Webb Telescope has observed that there are galaxies which are which were there before Big Bang. So what they are JWS or JWT, James Webb Telescope, is observed is the light. So as of now, they may not be existing, but at that time they were there. Okay, so I haven't picked that picture of the universe. They were developed by this Hubble telescope. So the universe, or picture of the universe. So it could be possible. So that was the Big Bang is a point. From that point, we started our evolution. From that point, okay, the universe, galaxy, this. So from that point, we are measuring everything. That point can lie before that. So okay, so if we are saying 13.7, our Big Bang, our universe can be more than that. So we can put that point before that. There's no trouble. Okay, so like if there is a like galaxies formed before the Big Bang, then Big Bang would have been happened before that. So like what we have observed by Hubble telescope is not very good precision or resolution. It will be better picture. Okay. So everything is based on our observations, right? Yeah. I think I gave my answer.
So is there any more questions from the audience side?
Can I ask a question?
Yes.
Yes, definitely, sir.
So I have the simple question. Like you were telling about the neutrinos, and they are pretty hard to detect. But what is the reason? Why do we detect neutrinos, and what is their application for the? Like, what could we do after detecting some neutrinos?
Yes, neutrinos are massless particles, right? So so one external neutrinos are massless, and other neutrinos like neutrinos are beyond external model, they are heavier also. Okay. So like
What?
we are,
1 second. What did you say?
I said that the neutrinos beyond external model, like BSM theory, heavy neutrinos also, like Will and stellar neutrinos, they are heavier neutrinos, right?
Mhm.
Okay.
Okay.
So what are the actual neutrinos? So what are their property? How they behave? As of from standard model, we know that the neutrinos are massless. Okay. And from Beeson theory, we know that neutrino oscillations. They exchange like up the tau neutrino to transform to muon neutrino and muon neutrino transform to tau neutrino. They can exchange when then through neutrino oscillation. For that, they have got the Nobel Prize. Okay.
Mhm.
What are their actual properties? So that we are
No,
for 5 times. Yeah.
I'm just asking, like, what is the application purpose of the detections?
Application purpose, I cannot comment because you say like why you are observing Quark-Gluon plasma. What is the application? There is no application of Quark-Gluon plasma. Right? But that is our understanding, how we understand our nature, our universe.
No, that's only what I'm saying. That okay, I made a detector and I detected a neutrino. So can I get some information about some galaxies, some planets, some or anything? Like just by detecting neutrino, can I get some information, some physical information?
I don't know because neutrino hardly interact with any matter, right? So it can be a better probe to draw a better picture of the universe. That is one point. Okay, because if anything interact with the matter, it will lose the information. So if anything does not interact with matter, then it is had all the information it was got initially. So it can better give a better picture of the universe. That is one point. Another thing that most of neutrinos in Earth coming from the solar sun. Okay. So the mostly are the solar nuclear neutrinos. So any like INO which is built in the Madurai, I don't know if it is operating or not because it's not my area of work. But yeah, so there are many contamination on those signals. Okay, that's why they are building the mountains and there are many layers. So like cosmic neutrino and solar neutrino, they are very hard to differentiate. But people are doing working on it. Yes, so therefore our understanding or better picture of the universe and understanding all the nature of the forces, neutrino mass is also one of the things. So
And
yeah.
and I'm also just interested, like, being provided a detector, how can you differentiate what is the solar neutrino and what is the cosmic neutrino? Because, like, once particles are detected, theoretically you can't differentiate a fresh made
No,
neutrino in
like then
laboratory
if
and
like any particle got detected, okay. So then either it is massive or not massive. So at
uh,
relativistic limit of mass and energy both are same thing, right?
yeah.
There is no difference yet. When square is equal to 1, I think you know. So E and M is both are same thing. So for masses we can differentiate how track will these are the experimental stuff. I don't know how they will do it. Okay. So neutron they are trying
Mhm.
to detect. And neutron actually not my area of research. So I cannot comment much on that part.
Okay, okay.
Yeah, Dr. Captain, there is a question from G. Balaji.
Yeah.
What about the spin of these subnuclear particles?
I guess I gave the answer.
Okay, thanks.
Um, okay, okay, then what is the evidence for the Big Bang? Uh, there is no evidence. That is a theory. They told that what is predicted that could happen in the Big Bang, that we have tried to observe in heavy anchораges, and there are many signatures which prove that QGP like medium exists, and QGP would have been present in the time of the Big Bang. So there is the one evidence. Then Big Bang is true. Might be true. Might be
There
true.
is a question from the Sampurna Das. Will our universe collapse on itself one day? If yes, what would be the reason for it?
Okay, you are talking about big crunch, something like that. Uh, I'm not that like appropriate person to answer this question. This is a question of cosmology, so those person can give better answer. I can give some theory, but I don't know it would be correct or not. So I would not comment on it.
Okay, thank you. So another question from the CV Gupta. Could we ever see all the way back to the Big Bang? I hope.
Yeah, we are increasing the energy like it is like 27-kilometer ring, and then other experiment plan that is at LSC that is called FCC, Future Circular Collider. So they are going to increase the radius from 100 kilometer or circumference 100 kilometer. So increasing the energy, they may look back much back into time, and there are many more things. So like what we know in the light matter is only 5%, less than 5%. Okay, 95% of the universe is in the dark. We don't know about dark matter. There is like 15%, 80% dark energy. then we do not understand at all. So there are many more things. So what we know is very little, and we are struggling to know more. That is our curiosity. We evolved from the 13 billion years. So yeah, so we will look into it if it is possible in this lifetime or not.
There's a question from the Babia. As we talk about parallel universe, so is this possible that we can find parallel quantum fluctuation, Big Bang, and therefore every universe have its own clock, I mean time?
These are the questions which are not my area of studies. I can answer, there is no problem. But these are the, like, theories. Okay, it's like parallel universe. Okay, there's the one universe has different time. If there is another universe, it would have different time. There are many theories, many things may or may not be possible. There are no evidence, and people are not working on the parallel universe.
Soumya Adisha Mishra. Sir, if the concept of parallel universe is possible, then is that possible as well that we can actually experience the Big Bang for the formation of another universe?
Sure, maybe. Why not? Like if there is parallel universe, then it will all will happen in different time zone. So maybe some universe, this present time, some big bang is happening. Quite possible. Who
So
knows?
one question from the Pervin M. I hope this is very good. It would be. Sir, could you recommended some books on particle physics?
Yes, there are many good books. One is Griffith, one of the best book for particle physics. Okay, and there are many Indian authors also. So I recommend Griffith, Introduction to Particle Physics. That is one of the best book. And one book is by Particle Physics in Heavy and Collision, Wong. His author name is Wong. My first name is Wong. C.Y. Wong. Okay. C.Y. Wong book. That is also a very good book. And there is one book by Big Bang to Little Bang by Matsuai and Yagi. There is also a very good book. Yeah. So we can post the book. I can give the name of the book in the group, so I can post there. So you can.
So, sir, it's my personal request to you that when you suggest the book, please suggest some elementary books so
Yeah,
that the college student could
Sure.
understand it,
Yeah.
rather than the
Yeah.
highly
No,
research.
that's why I said that these two books I said told are very basically very good books, like Griffith, very wonderful book, and C.Y. Wong is also very wonderful book. These two books are very useful.
Sir, there is some more questions. That what are the subdivision of particle physics area? Yes, I know one of them is chromodynamics.
Quantum chromodynamics. Quantum chromodynamics is one field. Supersymmetry is another field. The particle physics and the neutrino physics, electroweak physics is another field. Okay, and in quantum chromodynamics, there are many other sub branches. Like I'm working in the Quark-Gluon plasma investigation. Some people are working something else. There are many, just too vast. Just too vast.
Sir, please suggest the physics books for the school students. Sir will give the
Yeah.
list of the books, I hope. So Bhavya is asking one more question. Is gravitational physics can somewhat be related to it?
Okay, so as of now, we don't know because gravitational waves are simply the repulsion space-time geometry. Gravitational physics, as of it is not part of standard model, but in future it makes it like theory of everything. Okay, like people are working in quantum gravity, there are some aspects, but till now it is not with the standard model.
So
In
now
future, it may be.
I request all the audience to on their camera to take a group photo.
Can I ask a very simple question at the end?
Sure.
Is it like theories from the Western model, like effective theory or this quantum electrodynamics, we can use in a lot of other applications. It might be chemistry, atomic physics, and
Sure.
molecular physics, and even the finance derivatives, and so these theories are really like broad usable. So is it so for other theories like electroweak and QCD and others? Like, are they also applicable to a lot of other fields?
Yeah. That is okay. So quantum field theory actually. So when we talk about quantum field theory, so the field theory at temperature 0
Yeah, okay.
and no interaction. When we
Yeah.
incorporate the interaction, then we introduce the difference like quantum chromodynamics, the quantum field theory of strong interaction at
Okay.
temperature 0. Still temperature is 0. When we
Mm-hmm.
talk about the quantum electrodynamics, temperature 0. When we introduce temperature, then or masses, then we call it effective field theory and thermal field
Yeah,
theory.
okay.
So there are many, so things gets more complicated. So when we introduce one by one step, then it will get start complicated. And then the worst part is that quantum, like quantum electrodynamics, photons are non-interacting particles. They do not interact with themselves. Okay, so
Mm-hmm.
there is no complicacy. Only one photon, it interacts through electron to electron, electron to positron. That's it. But in case of quantum chromodynamics, gluons, which are intermediate particles, interact through quarks to gluons, quarks to quarks. They also interact with gluons to gluons. So gluons are self-interacting particles. So this
Yeah, okay.
self-interaction generates the complexity. Okay.
Mm-hmm.
So it becomes very complicated. So yeah,
That I
so there's a
understand.
thing. Yeah,
That I
yeah,
understand because, like, mostly these thermal QFTs are mainly related in. I'm an experimentalist, and if I do a thermal QFT, this means like all the fluctuations in my system, I am taking them very, very precisely. While zero temperature QFT, like, I am just neglecting all fluctuations which are like state zero. I'm just taking it; it's my ground state in zero temperature, while taking all grounds that are so-called in quantum optics, they call like vacuum fluctuations. So all the vacuum fluctuations, if I'm taking very, very precisely, so I will use this word thermal QFT, or
yeah,
so-called thermal states. I will use thermal states. But
yeah,
my
yeah,
question was, yeah, my
yeah,
question was like, being a QED, I cannot only use the QED in quantum optics, but certain other people, like people
yeah,
from the chemistry, they can use to
yeah,
interact, like how the
yeah, yeah,
photophysics and photochemistry is
yeah,
going on. So
yeah,
is it
yeah.
the same for other things like QCD? Can use certain other places also, like not just for the Quark-Gluon plasma, but can you use QCDs for
Yeah,
some
yeah.
other
No, so
macroscopic systems?
yeah,
Like,
no,
yeah.
no, no. That is what I'm saying. QCD developed from quantum chromodynamics, like strongly interacting matter, and the
Uh-huh.
strongly interacting matter, its range is very small, right? It's within the limit of the nuclear range. Okay,
Mm-hmm.
and like QET is the limit of electrons. Chemistry is based on the interaction of the electrons. How you have one atom of one electron is interacting with the atom of electrons of another atom, right?
Yes.
Electron from one atom, how it interacts with electrons of other atom. So
Mm-hmm.
QET is a theory of interaction of the electrons. It can be applied,
Yeah. Okay.
right? But the nucleus, one nucleus not interact with other nucleus,
Mm-hmm.
right? You haven't seen one nucleus like at the nucleus of the hydrogen and interacting the nucleus of the oxygen. You've seen it? Not. No. Nature is not possible. One atom is there and it is interacting through the electrons and found the molecule. So
Yeah.
if like one, two nucleus are interacting, then obviously you can apply the QCD, but still their nucleus interacting, and then inside nucleus you have neutron, proton, they are interacting, and within that partons are interacting. And
Mm-hmm.
strong theory of QCD is a theory of strong interaction. Okay, where the parton interaction comes into the existence. So for applying in general quantum chromodynamics, you have to make interaction between partons of one proton or from one nucleus and interaction of one parton of the one proton within different nucleus. It's quite complicated, it's not possible in that case.
Yes. So it's
Sorry
like
to
most.
disturb sorry to disturb the discussion as the time is running out.
Okay.
So the further questions can be put on the Google. We will
Yeah, I just
provide
like
the
to ask
Google
also
link.
one question. So what are the gravitons? Can you say something on it? Someone asked, just a quick response. Yeah. So gravitons are the quantum gravity fields, like GTR predicts the differential equation. And gravitational waves. So if there is a wave, there must be a quantum. So gravitons could be there. This being true, there is a possibility, but there is no finite evidence. That is my answer.
So
Over.
requesting all the audience to on their camera to take a group photo. please on the group photo. Sorry, please on the camera. Thank you all.
Thank you so much.
So, thank you once again to all the audience for listening to the today's lecture. I also thank the Captain sir for giving a very nice talk in a very fundamental way, so that everyone could easily understood. So,
Thank you so much, Deepak, and thank you everyone for joining me on this talk. Thank you very much.
okay, thank you. So we will meet in the next Sunday again with a new topic. So
Okay.
thank you once again.
Thank you.
Yeah, thank you, Dr. Captain, Dr. Deepak, and all members.
Hello, sir.
You can switch off the recording, Dr. Captain.
Okay.